Hello, so now we would like to look at the power of power function. For the purpose of this little video, I would like to distinguish power functions into two groups. I look at functions of the form x to the n, where n is a natural number, or I look at functions of the form x to the alpha, where alpha is a real number. Now, of course, natural numbers are real numbers too, so these x to the n's, in fact, are of the form x to the alpha also. But still, it does make sense to look at the x to the n format first. Before I do this, though, I would like to recall two important concepts, which is domain and range of a function. So given any function f, then the domain is the set of all values x which can be substituted into this function f. When am I able to substitute a value into a function and when not? So let's look at the domain of square root of x. We all know that the square root cannot be taken from negative numbers. So the domain is the domain of all non-negative numbers. Or in mathematical terms, we can write this as an interval. So it's the interval from 0 to infinity. Okay, and then we'll use this kind of bracket on the left, which means we include 0, but we exclude infinity, which is not really a number. The domain of 1 over x, well, we know we cannot divide by 0, but we can divide by any other number, if positive or negative. So this means all of r except 0, or in mathematical terms, we can write this as the interval from minus infinity to 0, and then the union from 0 to infinity. And here we use the round brackets to indicate that 0 is actually not included. Secondly, the range. The range is a set of all values which can be attained by f. For example, the function x squared plus 1. So we know x squared is always positive or maybe 0, but it is not negative. So whatever this is, it is bigger than 1, right? And if I substitute 0, I get equal to 1. So the range is all values larger or equal 1. And writing this in an interval notation, this will be the interval from 1 to infinity. For the sine function we know oscillates between plus and minus 1, right? And it looks like this. So here is 1 and here is minus 1. So the range of this function is the interval minus 1 to 1. But here is a very curious fact. So let's plot the power functions with non-negative integer exponents, so the x to the n's, for n is 0, 1, 2, 3, 4, 5, 6, 7, 8. X to the 0 is of course equal to 1, and the function, if I plot it on a coordinate system, is just the constant function 1. X to the 1 is the function x. It is a linear function and looks like this, of course. This is x squared, our good well-known parabola. X to the 3 is an odd function, so it has a negative bit here and a positive bit here. How does it continue? So here is x to the 0, x to the 1, x squared, x3. So here's x to the 4. It looks like a parabola, but it is a little bit wider in the bottom here. X to the 5 now looks again very similar to x to the 3. X to the 6 is kind of similar than x to the 4. X to the 7 then looks maybe a little bit wider than x to the 5, but it's again an odd function. X to the 8 is again an even function, very similar to the 4, to the 6, and to the 8. So if you look at this closely, then you have a pattern, right? You have all the even indices, so let's maybe mark them in orange. So this guy, this is all like concave up. They're all like more or less similar, whereas the odd ones, of course, they look also kind of similar. This, and this. They're kind of odd functions. And you can, of course, imagine how it continues. So x to the 9 will be like x to the 7, and x to the 10 will be a little bit like x to the 8, etc. So the domain, as we have seen, so for x to the n, what can I substitute? What am I allowed to substitute? So I'm allowed to substitute whatever I want. So the domain is the whole of R. Now the range is different. The range of x to the even, we have seen these are like the parabolas. We don't get negative numbers. So the range is 0 to infinity here. And here the range is minus infinity to infinity. So in the odd case, we go from minus to plus infinity, we get all the values, right? So here the functions look like this, and here these functions look like this. So power functions with real exponents. So now we look at x to the alpha. So now alpha can be natural numbers, but it can be something else too. And we know the basic rules. So x to the 1/2 is really square root of x. X to the 3/2 is the square root of x to the power of 3. X to the -2, this is 1 divided by x squared, right? And x to the -7 divided by 13, this is really 1 divided by the 13th root of x to the 7. Yeah, so these are basic rules for power exponents, which we should know. Let's plot these functions. So here I have these 5 functions and I have 5 plots, and I need to find out which is which. So the red one here is the famous square root function, so that would be x to the 1/2. And the green one is x to the 3/2. So this looks a little bit similar to the functions we have seen before with a natural number. And here, so the red one is 1 over x, which is x to the -1. And the green one is x to the -7 divided by 13. And then here we have an interesting function. So this is x to the pi. Right? So I said alpha can be a real number. Pi is a real number. So there's nothing wrong with looking at x to the power of pi. And it's a curious function because it looks maybe like a parabola, but it is not defined for negative numbers. So the domain is positive numbers, so 0 to infinity. Now a few basic calculus rules for power functions. So x to the alpha times x to the beta, this is x to the alpha plus beta. X to the alpha to the gamma, this is x to the gamma times alpha, so the exponents multiply. X to the minus alpha, as we know, is 1 over x to the alpha. So these are super duper important rules, and we will use them all the time. Finally, just quickly about polynomials. So polynomials are made out of these terms x to the n or x to the n minus 1 down to the constant case. And the coefficients an minus 1, they are just real numbers, etc. So they are real numbers. So examples is 17x to the 6 plus 3x plus 1, or x plus pi x to the 7 minus root 2x to the 9. Interesting is what is called the leading order term. So here this is the leading order term, and then we call a polynomial to have the order n if the leading order term is a to the n. So this guy has an order 6, right? So the highest order term is 6. And this guy is a polynomial of order 9, because the highest order is 9 here. It doesn't have to be an order, so the higher order can appear somewhere, not at the beginning, but maybe somewhere else along the line.